So let's talk about another tricky problem, another tricky application of the fundamental theorem of calculus, part 2. Let's try and find the derivative of the following function. Now this function has sliders on both the left and the right limits of integration, both bottom and top. And we're asked to find the derivative of this function to apply d dx to this function. Now, just as before, there is something in this setup that is preventing us from applying fundamental theorem directly. And the big issue is this lower limit of integration. In the theorem, the lower limit of integration was supposed to be a number. It was supposed to be constant. However, here we have an issue of this lower limit of integration being a function of x. So here is what we're going to do to rewrite the problem so that we can apply fundamental theorem to the problem. And it relies very heavily on those properties of definite integrals which we discussed several days ago. To begin with, I'm going to take this integral and split it apart as two separate integrals. I'm not going to integrate all the way from negative x to x. I'm going to take a stop along the way, and I'm going to integrate from negative x to 0. Now I have just chosen 0 because I like 0. It's usually a very convenient number, but this same process will work if you put any constant here, any constant. Now, having taken a rest at x equals 0, I'm going to continue my journey and integrate from 0 to x this function. Now this is lovely because the right-hand integral, the right-hand term in this expression, is something that I actually can differentiate using the fundamental theorem. It's in the perfect format. Bottom is a number, top is x. However, this term on the left-hand side still needs some work. I at least have one of the limits constant, but the bottom limit is supposed to be the one that's constant, not the top limit. So what I'm going to use now is this property which says that you can reverse the order of the limits of integration so long as you flip the sign of the entire output, So I'll put 0 as the bottom limit at the cost of putting a negative sign as the output of that entire integral. Now we are in a position to be able to take the derivative of these two functions. The right-hand side, the derivative can be found very straightforward manner just by putting x into t's position. The rate of change is equal to the output of the function at x. Now for the left integral, we'll have to use the same trick that we did in the previous example. Put in the top function in the position of t, but then, because of chain rule, don't forget to multiply by the derivative of the upper limit, the upper function. So, as a result, we get -1 times -1, the derivative of negative x. Because we have all even powers in this denominator, we get x to the 6th plus x to the 4th plus 1, since an even power of a negative quantity is the same thing as the even power of the corresponding positive quantity. And then we have two identical fractions that are being added together. So, after simplifying, we have two copies of the reciprocal of x to the 6th power, x to the 4th power, plus 1. and that would be the rate of change of the area under this function as we slide both the left and the right hand limits of integration. This is the general process. Take your two-sided limits, if they are both functions of x, split the problem into two separate integrals by putting an intermediate constant between the limits. In our case, we chose 0.